I accidentally missed my the regular examinations because of medical emergency. I mailed you regarding that as well, even the WITP support as well.
In that case, if you have missed your regular exam, then you can approach to the operation coordinator seeking
Huh.
for the makeup exam. I think you can.
Okay, sir. And sir, the structure of the question paper will remain as it is, or we are going to means you will introduce whatever you are going to cover today, or something like that, sir.
There'll be slight change because hardly a matter of some concept. So
Okay.
something that is being covered in ninth contact session will also be a part of the midsem. Obviously, it should be. That is justified only.
Okay, sir. Thank you.
So yeah, thank you. So should I mute myself, sir?
Okay, sir. Yeah, so I think if there is no further question, then we can start for our today's class.
Yes.
Okay, yeah. So, students, today we are going to cover one of the very important concept that is related to embedding side of the graph, because embedding is meaningful when it has a discriminative power. And how to create the maximum discriminative power, that is the overall actually aim of this entire GNN class. So in that area we will see one of the method where we will be actually learning the new embedding of the graphs. So before starting that, are you able to see my screen, one blank page screen?
Yes, sir.
Okay. So, like previously in some of the your initial classes, you have seen some of the method through which also we have tried to embed the graph. Increase the size. And okay, one instruction. So during our class, I am actually not looking at the chat window because it's difficult to look both at a time. There's a shared screen and the chat window. So in case if you have any doubt, feel free to ask me that question at that point of time itself. So for that, I have unmuted you all so that you can unmute your mic and you can ask me questions. So like in our initial classes, we have already seen various methods which actually encodes our structure of the graph. So like suppose this is the graph. So naturally graph will have some nodes and the edges in that. So this kind of something, some structures will be there. So in that, like a centrality, one of the things that you have studied. So centrality here itself, if you see that if you are try to find the centrality of any at the node level. So node is naturally connected with your various neighborhoods, and each neighborhood is again connected with some of the other neighborhoods. Like this, it may happen. So for suppose this is my node of the interest where like I'm trying to encode this their embedding. So embedding is nothing but it is the representation of the node, like how it is around with its structure. So in that, like when we have studied centrality, so centrality is nothing but we are trying to understand the importance of this node in this entire network. So importance based on their network positioning. So based on the network positions, we have encoded. So in that, like you have studied between the centrality, cut centrality, or the page rank. These are one of the important algorithm that we have studied. And each one will have a different ways of encoding their importance. So the moment we encode the importance, and suppose this one itself we provide that as their embedding means the value. So like suppose it has 3, something like that. I'm just giving some hypothetical value, one single number. It can have a multiple number as well. So suppose like 1.5, it can be fractions also. So each one is your embedding of this graph. So means this node can be identified by using this property. So this is the way we are doing it. So this is the one of the way of doing your handcrafted method, it is called. So handcrafted, there are many other ways also. I'm just giving you one example just to correlate exactly what we are trying to do. So in the centrality we have studied. So that is one of the method, and this is also termed as feature engineering. So in this feature engineering, based upon the rule set, whatever the rule we know, so those things we want to encode it, and that one give that value as their embedding. But in a very large graph, if you try to do these things, then you will have a lot of computational overhead and almost impossible to handle the large graph. So that is why at that time it was felt that we need to have some automated method also of finding these feature sets. So till now we have seen the handcrafted method to generate the feature set of the nodes, or it could be not only nodes but for the links also, or as an entire graph as well. So for this entire graph itself we can create a encodings in this. So where the main idea was that based on structural property, two feature sets should be closer if a structural property is same. So this is very important criteria, that whenever we are trying to encode it, because here also if you see what we are trying, like suppose this one u1 and this one u2, both if we are getting a almost similar centrality value, means their structural behavior around this is same. This is what we are telling, and that is exactly the aim. Like whenever we are creating any embedding, means structurally all the nodes which are the same or very similar, their embedding also should be similar or same. So this is the constraint that we are giving. So the first rule is that constructing handcraft. So you always keep in mind, like whenever here we are talking about the feature set, means we are not talking about their some node property based, some of their assigned embedding, but based on the structural behavior, what kind of the embedding we can impart. So that is where this is what it will be automatically, it will be learned. And here, this is the constraint we will follow, that wherever a structure is same, that means their embedding also should be same. So based on this, we will try to understand that. Okay. And since it was computationally expensive, so to overcome this, we want a mechanism which will automatically extract the features which is relevant for the graph. Handcrafted features extraction is called feature engineering, as I said. And when we were extract features automatically, then that is called your graph representation learning. So Handcrafted whenever you do, that will be your feature engineering. And if you extract automatically, so why previously it was called engineering and why it is called learning in the automatic side? Reason being in that there will be some parameter which will be learned based upon your given data set. So that is why it is learning. But in the engineering means we know the rule set. So based on the rule set, we are crafting like what could be the embedding value. So that is why that is called the engineering. And whenever you have a graph as an object for which we are doing it, that is why it is called graph representation learning. But in case in a general sense, you may have other topic also might have heard a lot of time that is called representation learning. So representation learning is the generalized one where this representation learning could be for your image also, or it could be for your audio, or it could be for your visuals or anything in that. So that there also we are doing that through the deep learning method. That is your whenever you have a Euclidean space problem. Euclidean space means when your structure of the data set is almost fixed. So you know that it will be a linear data set or it will be a matrix data set. So those kind of things are whenever fixed. So that is called your Euclidean space problem. And whenever we are doing the embedding of those objects, so there also we have a similar thing, like two similar object. If like suppose there is a image of the cat, there is a two cat image. So naturally there also embedding should be same. If it is a cat, embedding should be same. If it is a cat and elephant, then elephant embedding and the cat embedding should be different. And since they are both animal, but suppose between cat, elephant and human, so naturally human is not belongs to that animal kingdom. So naturally humans embedding will be far, far away from those things. So that way, so based upon that, how they are closely related and how they are separated. So based on that, you are giving some values. So those values can be handcrafted. Then whenever it is handcrafted, that is your feature engineering. Whenever you are doing automatic learning based upon your input data set, then that is called a representation learning. And we are very, very specific about the graph because graph is your non-Euclidean space problem. Non-Euclidean space problem. So this is the non-Euclidean space whenever we are dealing. So that is why it is called GRL. So GRL, this is what today is our topic. In this, we will try to understand exactly what kind of methods we use, what is their advantage, what is their disadvantage. So those things. So any questions on what that this topic is and what we are going to discuss? You can
Sir,
say
one
no
question.
if no questions.
Sir, one question.
Yeah.
When you mentioned that in GRL we will have different weights that has to be learned. So,
Yes.
like, is it the similar to like something back propagation? How we learn the weight parameters for the neural networks?
Back propagation is the next level. So here we will see some shallow methods. That is what. So back propagations whenever you are doing, so that will comes under your deep learning. So that is the next topic that we will be covering it. Okay. So here we will not use the back propagations because whenever you are doing the back propagations and you have multiple layers, because whenever you are doing this back propagation is like in this ANN kind of things, just assume. So you will have a multiple layers through which your data will pass. This is called forward and this is called your backward. side where we are adjusting the weights. So whenever these kind of methods we use, that comes under your deep learning side. That is why it is called deep learning, because layer by layer we are creating it using a neural network. So here we will not create actually a neural network. Okay.
Yep. Thank you, sir.
Yeah. So if no further questions, then let's start our topic of GRL. Just give me a minute. So let's first visualize the vector representation. Something like this graph, and suppose this is my U is the node for which we want to learn. Here I am always giving node U as an indicator, but it could be your edges, it could be your entire graph, anything. So just to simplify the description, I'm just using a node for this. So in this case, like suppose I want to create a function for the node U, which can be written in the real space of dimension D vector. So that means what we are trying to say, that there will be a d-dimensional vector. So vectors, whenever we say vectors, it will have a multiple column, but one row. So that's the definition of the tensor. So if it is vector mention means it will always be a one row. If it is a more than one row, that will be a matrix. So here x1, x2 like this. Since it is the d-dimensional, so up to xd it will go. So this is what it is called a vector. So this is the vector tensor, or you can say this is the vector of means of single row matrix. You can say also these things. So and this is my input graph. Okay. So here we need to define function f, which will read input node u and transform in d-dimensional real number vector space. This vector space can be used for various downstream tasks. So what is the purpose of doing this? Because GRL is involved up to this one. But what is the purpose? Like whenever we have this one, then these things we can use for various downstream tasks like node classification, uh, link prediction, or for your graph classification. Like in the webinar also we have discussed, so almost similar kind of the task. So like anomalies distractions. String. Why we can use it this one? Why not this one directly? Can you say, any one of you? Hmm? Why we are using this embedding, not directly u initial value? It could have some initial value also, right? Which we are transforming it. So initially, like suppose it is a single dimensional vector, and suppose it is the value 1, and this one I am transferring to the d-dimensional vector space. Why we are not using this one? Any answer? Anything? Yes, no, don't know.
Maybe because of the size of the like the overall sample, because uh, in the beginning what we have the vectors which is huge and also not structured. I'm just guessing.
Means actually here I'm getting confused from your statement. So when you said that in the beginning we will have a huge unstructured vector,
Graph.
right?
Yeah.
What exactly this means over here?
I mean the real world data, like real world graph.
This is the real world graph. I'm telling you, okay, this is a 3 node. Let's fix to this representation. This is the graph we have. This is my initial embedding, and this is the after embedding. So something like a point, let's say d-dimensional here, I'm fixing it to 3. Value 3 means you will have zero point 0.5, suppose it is 1.0, something like that, and it is something 0, 0, 1, something like that. So this is the vector we have. I am telling I will use this vector rather than this vector for downstream task. Question is why? Because if you will use this, then it is good, na? We don't need to do all this clumsy task of so much of mathematics and computation. Let's directly use this. Why I am first transforming it and then using it?
So that, sir, we can represent each of the node in some generic vector space, which can represent each vector space basically represent the properties related to each node, so that we can make similarity or anything.
Partially getting closer, because this one is also property related to each node.
But it
This
is
is
only,
also.
sir, yeah,
Mm.
but it is only, sir, representing the number, the 4. But say when we are representing like 0.5, it may gives a more clearer picture to particular properties of that node,
Or
which
also
Getting
maybe
closer,
the
yes.
neighborhood of the neighborhood nodes.
Now you are getting guys closer. So that is what in the beginning of this introduction session I have used discriminative power. That word I have used in the starting itself. Discriminative power means, like suppose if you have a 3 class, then whatever the output through that pipeline, whatever you create. So this embedding should have a more discriminative power, means my 3 classes easily separable by using this rather than this. So naturally, I will not, this one is my initial one, this is my final one. Suppose through pipeline I have generated these two. I have a 3 class. So if I will use these things for my downstream task, means suppose a class labeling itself I'm doing it. After that I will use simply a softmax and say, okay, which class belongs to this one. So highest probability, okay, this one looks like very easily I can say, okay, that class it belongs to. Here it is, you cannot do that. So this is what, so by doing this iterative methods of transforming your initial embedding into some another dimension vector space, you are taking it. So, and the reason of doing this is that you are increasing your discriminative power. So whole purpose of this entire subject itself is that how to increase this discriminative power. Because the moment I increase the discriminative power, I have a less number of false positive and my accuracy will be high. So whatever be the task, we are doing it. So everyone requirement is same, that we need final output such a way that we can easily separate for this. And that is the entire purpose of this doing all this activity, right? So simple word in a simple sentence, one sentence answer, it just increases this discriminative power. That is why we are doing it. So now you are getting sense out of that, like why we are transforming it, what is the meaning, right? You are able to correlate with your machine learning task, how it will be closely related. So in this similarity in embedding, like suppose I have now two embedding. So embedding is represented by suppose Z. So Z U1 and Z U2. Suppose for the two node, we got this two embedding. So similarity in embedding also indicates similarity of node in the network too. So based on the network structure, suppose if those two are very similar, very close, means their property will also be close. So, and this is what exactly is the initial assumptions also we have said that about setting up the embedding. Because initially, suppose if you initialize any of the algorithm with some random value, definitely we will get some embedding, but whether that embedding is meaningful or not. So that constraint, we do it by using this similarity based constraint we deploy on that. That will make converge of this your initial embedding to some final value. And unless until it is not converge, it will not have those discriminative power. So convergence will happen always based upon your network similarity. So network similarity, this sentence. Just a second. So this is the base idea. So what exactly will be the steps? So process of embedding. One of the technical term we use that is called encoding. So process of embedding is also called encoding the network information. So what could be my like a node embedding framework? So now we are shifting a gear little bit. So initially introduction we have understood where we have generalized, but mostly we represented our generalized information in terms of node. But now we are getting to the node specifics. Like suppose if we have to embed the node or embed the edges or embed the graph. So definitely there will be different process to do that. So here node embedding framework we are studying now. Node embedding framework means the rules or the process that we are going to follow. So first one is step will be your encoder, where we will encode it, the node similarity function. Decoder. So this decoder will be used to decode the encoded information. So let's see each step in detail. Encoder means process of r-dimensional vector in the real space to run node similarity functions. So it's about this one. What is that? So in original network, we need to define node similarity functions which measure the similarity in original network. So in original network, if nodes are similar, then the function should be capable enough to defining it. Those things means identifying the similar nodes or dissimilar nodes. Third one is the decoder. In the decoder, actually, we maps the embedding to similarity score. So naturally, we map it means we have to do the optimizations. So optimization of the parameter will be required. Optimize the encoder so that suppose this is my function, I'm just writing it. similarity u and v. So this functions actually find your similarity score between these two nodes. So this should be also similar to, if I try to find the similarity score between those two, this is nothing but a dot product. Okay. So their dot product also should match with this similarity function. So here what exactly is happening? So like suppose ENC is my encoder function. So that operates on U and this generate embedding ZU. Okay, so this is about a similarity in original network. Okay, and this one is embedding space. So in the embedding space, this is my similarity. This is in the original network. This is what encoder will generate this. So now we will go to some specific method. So here in this class, we will study the two kind of the embedding. So first one, random walk. Second, node method. So these two will be the method which will be area of interest of our today's discussion. So any question till now in order to understanding the framework and what is the meaning of each steps, what we are trying to do? Any questions? And this notes will be shared to you after this class. So don't worry about these things. You will get this. So any questions? Yes, no? Or if yes, then what is the question? All clear?
Yes, you can go ahead, sir.
Okay, thank you. So now see step by step these algorithms. Okay, before getting into this random walk, let's understand one more concept that is about the shallow learning method. So, and what exactly is some of the drawback also of this method. So first understand that, then we will get into the detail of this method. So when size of embedding vector D, and suppose we have some n number of the nodes, then all will be stacked in a single matrix Z. So in this learning, how we stack the information? Sorry. There will be actually matrix, and in this each column, suppose this is one of the column, and V is the vector space. So this side will be the d-dimensional vector space, and this side is your n is the number of nodes we have. So for any node n I, we will have d-dimensional vector that we have. Okay. So entire learning can be embedding will be element of d cross v, where this is the number of the node. So in the single matrix, we are storing all this information, the encoded information. So here each column represents one node embedding vector. Since embedding is lookup on matrix Z, so this is called shallow embedding. Why it is called shallow embedding? Now you understand that whatever the embedding that we want to get. So this is nothing but this is the lookup functions. So based on this, which node we want. So we just give that node number. So that lookup will happen on this matrix and then we will get the embedding of that. So that is why it is called a shallow embedding. And that is where today we will be focusing on the shallow embedding, and going to subsequent class, we will be moving to the deep learning side or deep learning based embeddings that we will understand later on. So this is called shallow. When size of graph is large, suppose billions of the node, then 10 to the power 9 order, this one, d cross this size. So you can imagine that it is almost impossible to hold in the memory also, this kind of matrix. So for each element of the Z is representing, that needs to be learned. So then the size of Z becomes a issue. So that is one of the disadvantage. Like for the very large graph, still this is not a very scalable solution. Okay. So here objective function is to maximize. So what exactly we will be doing? So we will be maximizing this one. So this will be our objective functions. As per the similarity functions of actual network. So decoder is designed based on the similarity function. So similarity functions is the responsibility of the decoder, where we will be maximizing this. So similarity functions can be defined based on the many criteria. So here, like one of the obvious methods, like nodes are linked. So which node is linked to which one? So based on that, or the shared of the neighborhood. So between these two nodes, how many nodes are shared? So based on that also we can give the similarity score or have the similar structure. So similar structure like one hop or two hop. So based on that, what is the level of similarity between the structure of that? So based on that also you can define your similarity functions. So here, let me write this. So similarity functions can be defined based on many criteria. There can be many other methods as well, but these are some of the important criteria that we need to understand. So based on that, we define our similarity functions. So here nodes embedding is the task independent functions and we do not use node label. So here you can see now embedding is completely your task independent. So it doesn't matter like initially whatever the task we have given. So any of the task you perform. So if you're doing for the node classifications, then it doesn't mean that your a random walk or node to wake will be different. So those methods are actually your task independent. So whatever the based on this learning, you can do any of this task. So that is why it is called a task independent also. So here node embedding is task independent function. We do not use node level. So they initially provided node label based on their some uh, non-structural based some properties like some chemical compositions or some other way of embedding, because you can do the embedding in various ways. So those things we do not consider. So those labels we usually avoid on the node feature set. So our aim is to create node embedding which captures some aspects of network structure by encoder. This embedding can be used for any task. So here the embedding is the task is for some aspects of the your network structure. This is what we want to embed. So one of the best way I will say for understanding, like whatever be the big size network, initially you give some same value. I will say let's say 1. You give all the node initial value 1, then start encoding it, because based on their structure naturally you will get a different values. So that is where your structural encoding will happen. So there are various ways of initializing this initial embedding, and then you can use it in just one of the method, like if initially 1 or use some of the other criteria. So those things you can use it for defining your initial embedding value. Okay. So now come back to our algorithm that is called a random walk approach. Or you can say this is also termed as a deep walk. So what could be the random walk mean over here? First, let's understand that in any large graph, just assume that this is node U. From here, you have a based on their degree, like these many options you could have that from here, and suppose this is V is my target node. I want to reach over here. So what we do, we take in a random walk approach, what exactly it will happen. One of the approach I'm telling you, because random walk can happen in a n number of ways. One of the most simple one, let's start with that. So from here, I can take any of this with equal probability. Suppose it is a probability based. So based upon your number of possible options, you can define what could be the probability. So here, like suppose 1, 2, 3, 4, 5, 6. So naturally 1 by 6 probability. Since each one has a 1 by 6 probability, that is what it is called a uniform distribution. So uniform probability distributions, this is what we are using it. So in that, like suppose I picked up this. From here also, I have n number of options. Suppose from here I move to this, then move to this, and each place we will have this. So naturally, always you have a star structure in that. So this way we are moving it and we have reached. And here, like suppose we cannot fix the destination, but we can say like number of hops. Like here, 1, 2, 3, 4. Like suppose in my algorithm, I have defined, because this will be the hyperparameter, number of hops that we want to travel in that big network. So I say 4. From here, I have just started. I have moved to this. This is 1 hop. From here, I have got, this is the 2 hop. From here, I have gone to this. This is the 3rd hop. From here, I have gone to my 4 hop, and this is the landing positions. So from U, I have moved to V using this 4 hop in this uniform. So naturally, next time if you do iterations, if you pick this one, naturally you will land in some different position. So this way, in a large graph, instead of traveling to this entire graph and then trying to encode the network information, we rely on this network work. And here now you can easily understand the beauty of this method. Like suppose if any of this side, if um, you can say the higher probability, because probability of each root is changing. So naturally, where like you have a less number of degree, so means it is high chances that you always converge toward that, because their probability is high. So that way you can understand that what kind of the structure it has, and you can encode that structural information based upon your random walk. So that way you will get a lot of computational advantage, because you are saving a lot of computational effort in order to just doing some sampling. So it is not just one time you do it. You do it 10 to the power 3 or 10 to the power 6, this kind of the time, so that what will happen, you have also read in your statistics class that probability is also actually converging functions. So based upon your number of trials, after some trials, you will see that the probability of that event will be fixed. So here also exactly same thing happens. The more number of trials you give, then you see based upon their actual probability, actually that will always be converged like that. So that way you will understand that what kind of the structure it has. So this way we do it. So now understand like mathematically what exactly we are doing and how we are encoding it. So first one is the random walk strategy. So you understand the random walk. Now getting into the detail of this algorithm. So step 1. We have, okay, 1 more hour we have. Okay. So a random walk strategy. I have given you one of the example of this random walk. Can any one of you tell me some different random walk strategy? Because you have already studied this graph data structure. So I am very much aware. I am assuming that you might be aware of the other random walks methods. So Can any one of you tell me what could be the other random walk strategy? Any guess? What would be other way? I have explained you about the uniform distribution method. What could be the other method? Hmm? Yes, any wild guess is okay. Yeah.
Professor Vipin, Ravinci has replied something on message.
Okay, actually, I'm not looking at the message. 1 second, please. Page rank. Page rank, how it will be a random walk method? No? Yeah, partially we can take. Okay, we can convert this page rank in a random walk strategy. So, okay. Any other guess? Very generic one that normally you use that. And if you can speak, that will be fine rather than writing because it's difficult to track the chat. Okay, so I'm telling you BFS, breadth first search, DFS. So suppose if we start with this kind of method, in that, okay, like I have suppose 4 hop I need to take. First hop, I will do BFS. Then I have some probability functions. So BFS, then some probability functions with which we select one of the node based on this BFS because BFS will give me different routes. Then I will take DFS and again some probability value so that we will create some biasing also in that so that it is not a uniform distribution but some biased one. So what exactly this means? Whenever you are doing the BFS means looking at your micro level details. So how beautiful it is that just understand. So suppose this is the U and micro level means just near to this node, how this structure is. This is what you are looking. And in that you have moved, suppose this side. And after that you are looking at the DFS means you are looking at the macro level. Micro and macro. These two things also we can mix so that it will give you a good view of your travel. So what exactly is the structure as the microscopic as the macroscopic as well. So this is the different strategy. You can adopt many other ways of doing it where like some probability functions you can use it. So whatever be the random walk method, you can use it. So whenever we are doing it uniformly distributions, that is where it is the random walk. And if you adopt this kind of things, then it will be called a node to peg. So this one we will see it detail as a next topic. So this is the importance of the random walk strategy. So as a step one, we have to first fix the random walk strategy. So what kind of the strategy we are going to adopt? So we need to fix how randomly we are going to walk over the graph. One of the simple way can be pick randomly some node and choose randomly some next node and keep on walking till predefined fixed length not finished, means number of hops that we are trying. So as long as it is not fixed, you just keep on going it. So that way you will have a list of node that you will be traveling in. And what we are doing as a step 2. So first one was the random walk strategy that we have fixed. So based on that, we have started traveling. Second step, what we are doing. So we need to randomly initialize some initial embedding vector that we will be initializing it. So that is the ZU vector of length D, real value which will be optimized based on the idea that similar node will have closer. So whatever were the embedding that we are initializing it, so that will be optimized so that similar node will have a similar embedding. So this iterations we will do it. Point number 3, probability of reaching node V from U using random walk strategy R will be multiplication of each step as all hop is independent because it's a random walk. So each hop is independent. So that is why you can say probability of reaching node V from initial embedding U. So this is the conditional probability that we are using. So you can write it like suppose intermediate nodes are this one from U, it has gone to VI, probability of suppose I, this is the J, sorry, J node, it is going to the K from Vj, initial one. And suppose it was the 3 hops, so 3 probability I'm writing it, otherwise based upon your number of hops that they are using it. Okay, Z K. Sorry, ZV K. This one. So you can write it as a multiplication functions. So this is will be your similarity functions. So if we take log likelihood, then we can generalize and write it as a summation functions. U is the element of V log C. So neighborhood based upon your strategy R that we are choosing. So use the neighborhood based upon your strategy R, and this is the initial value that we are getting it. So this is because the moment if you take the log, then it will be a summation functions. So this is what the summation functions log likelihood we are representing it. So in this way you can write the similarity function. Fourth point, if random walk is probability of some node occurrence is high, means they are closer and considered as similar. So that is what I told, that probability of reaching to same node each time means they are very similar, a similar node. So that is the basic definitions we are giving because we are using the probability function. So probability of two node is same means that node is similar. So from the random walk. So this is what we are giving it. So we will write this point as well. So in random walk, as similar because based on the probability value we are giving them which node is similar or dissimilar.
Sir, one question.
Yeah.
Like when you say the probability of two nodes are same,
Hmm.
what exactly it means? Like the walker is on that node, or how do we find that?
Yeah. So like as I said in the beginning, like suppose on the same node from where we are traveling, so and probability of reaching the each node. So this is what we are computing by using this probability function. So for the two node, suppose the probability is almost same, means the nearby structure is same. That is why you are getting a similar probability value, right? And if the
Yeah,
structure is same, yeah.
but then in that case, here we are just seeing kind of how reachable these two nodes are from a particular node, right? And then we are
Mhm.
giving them, assigning them the same probability. But
Yes.
there could be a situation that these nodes are of completely different category, like maybe heterogeneous graph,
Mhm.
right? Then in that case, how do we still give the same probability, or like
No,
we'll
no,
deal it
see,
differently?
first of all, as I said in the beginning, we are dealing with the structure. So always assume a plane graph of the structure. So we are interested in the structure wise, how similar they are. That is the whole story of this GRL. Okay. So just consider the structure, forget every other detail of that graph. Okay. So based on the structure, if two node has a similar structure, so similar structure means it could be based upon your strategy. So what kind of the structure you want to get. So how you are defining that structure. So here also like a similarity, here I have given you the various criteria.
Mm.
Which one you want to use? Like nodes are linked. That also could be one of your similar structure or share the neighborhood. So between these two nodes, okay, how many nodes are getting shared or have a similar structure around that role, structural role means like the pentagon, some or hexagon sign kind of things is happening around that. So those kind of the roles we can take it a structural role it has. So those things also we can use it. So based on that, like how exactly we are looking. So here we are using one specific method. So through the random walk. So in the random walk, we have traveled with a uniform distribution. And naturally, when a structure will be similar for these two nodes, means the traveling structures, the connectivity and all, then only we will get the similar probability. Otherwise, you will not be able to get it. And probability is not just one go. Like it will be trials may happen to determine the probability, like 1,000 times or the 1 million times you are iterating. After that, you are converging to that probability value. And you also know that probability converges when your number of trials
Correct.
increases,
Right.
right?
Because the
So
certainty will increase and the routing will be much clearer and better.
exactly. So you don't assume that one single step I have gone, then I will give this two nodes similar. No, you have converted 1 million times of that trial. After that, you are saying no, this two nodes has getting a same value, means their structure is same. That is what you can say,
So, sir, one
right?
more question related to
Mm,
this. So, suppose
mhm,
if we have a huge graph and
mhm,
there are two subgraphs which are located at completely isolated different positions,
mhm.
and I'm just trying to think that in that case, this random walk, will it give the similar value or will it give the different value for these two subgraphs?
Similar value if their structure is same around that, because the number of hops also different. So like suppose u and v is suppose if a diameter is suppose 100, I'm just talking some imaginary number. Normally
Mm-hmm.
100 diameter means a very sparse graph it will be. So in that 100 diameter away, so and suppose both the node is around 100 diameter away, okay, so they are the farthest point. So in these two nodes, suppose 4 hop steps you have conducted on these two nodes.
Mm-hmm.
And if there is structure around these two node U and V, if it is same, then naturally your probability functions will also converge to the same value for both the node. And you can say, okay, both the node is similar.
I see. Mm.
Okay, are you able to visualize?
Yeah,
Let me
I'm
see.
able to understand, sir.
Yeah, so see, like suppose this is some 100 diameter. So here is U, this is V. Okay. And
Mm-hmm.
here and diameter is 100, suppose. Now you
Mm-hmm.
understand what is the meaning of diameter. So
Mm-hmm.
I will not get into that. So in that, naturally here also will be some local structure will be there around that.
Mm-hmm.
And here also some local structure will be around that. And suppose in that, this is my starting node, I have conducted uniform random walk I have conducted 10 to the power 6 time. And here also I have conducted 10 to the power 6 time. I have just moved three up or something like that. So naturally you will get some similarity score for this node. Okay. And here also you will get some similarity score of this node based on that probability distribution that we have talked. So if there around that, if structure is same, then whatever by the embedding that you are getting z of v, and if you compute z of u, then they will come very similar. Okay. If their structure is same. So similarity functions of uv. Suppose this is my original some functions we have defined. So this score and this score will match. And in fact, we are forcefully matching it also. So that is what later on you will see that how we are actually using this guided functions for this one. Okay.
Okay, sir. Thank you.
Yeah. So this is about the fourth point. So one of the very common method like dot product, we can use it to define the similarity functions. So as I have written in the previous line as well some time back. So this one, so this is nothing. You can visualize like this. So this is ZV, this is ZU, and this is their distance. So how far they are. So so here R is your random walk strategy. So based on that, you are getting some probability value. So this one you can, so So we can use cos theta as the encoding function. So this cos theta is my encoding functions, where what is their value. So that one we will use it for the similarity checking. So our objective is to learn d-dimensional embedding vector that preserves the similarity. This is what I was telling. So we will define itself that our objective is to learn a d-dimensional embedding vector that preserve that similarity. And here, if nodes are nearby, then their embedding should be similar. So nearby nodes, like between that, how distant they are. So those kind of things also we can use it to find that, okay, these nodes are similar or dissimilar. Okay. So this is point number 6, is that our objective. Your similarity will always be preserved. So in this way we are computing it. In fact, our mathematical functions will be defined based on this itself. So say, like, let we have a graph which is represented by nodes and the edges is the graph. Function that transform your U into d-dimensional vector. So F equal to ZG. This is what we can write. It's number point. Yes. Maximum is log likelihood. Maximize function set. And this can be written as that is equal to log likelihood of probability Okay, so this is your neighborhood based upon your strategy R for the U. So this is what we have to maximize. Means if they are similar, then your log likelihood also should be maximum for those things. And here one important thing to note, like NRU. Multi-set because of strategy R. So based upon your strategy, multiple times you will say that same neighborhood is coming. So that is why it is called a multi-set. So it is not exclusive always. Now our problem converted into optimization problem. So now you can see this is the optimization problem. So what is the loss functions that we need to minimize? Suppose this is the loss functions. So here U is the element of P, and we have to do summation of V, which will be element of neighborhood based on the R U minus. We are using minus 2 because we have to convert it into the minimization. Maximization is converted into minimization. Okay, for the given fixed length. So this is the loss functions, that is the minimization problem. We have converted it. Similarity probability can be defined using softmax functions also. Softmax function. So this was my similarity function. This gives the similarity score. This dot. So softmax functions how will they write? This one we can write it exponential element of your node set V. So this is the another way we can write it. So this is the summations over this one. And so this is will be U. We are plotting between U. So between U and V, we are doing at the weighted average. You can see. So for that, we are using softmax functions. So this is giving me probability of these things. So now we can write it as this one will be your probability with the strategy R for V given U. So these two similarity functions, we are equating it. So this one is your similarity functions of actual network. And we said if those are similar, then their score also should be similar. And this is the node embedding similarity functions. Okay, so now optimizations functions we can rewrite it. What exactly we will change? So here actual one will be replaced with my node embedding functions. So once we will replace this, then how it will look like. This is step number then 11. One number 11. Now optimizations functions. So this is your minimization function using your node embedding similarity score. So in this, can any one of you see what is the biggest computational issue in this loss function? Any one of you can guess? Where exactly is the problem? Because it is computationally very expensive. This is my statement. Now question is why?
The dot product.
Dot product of this one.
Yeah.
This is a d-dimensional vector. So this could be like suppose 20 cross 20. I don't think that will be a computationally expensive thing. Any other place? Just look in this equation carefully. Look. Look the summation side. You see any issue?
I think when we do the summation and then on top of that there is another summation. So it
Exactly.
reiterates for like double loop and that too also for n number of times, then v number of times.
Exactly. So this is the nested summarizations means here what happens like whenever you travel from one node to another node, then each time you have to travel this entire graph because to calculate the softmax functions, you need to travel the entire graph. And if you see complexity, then it will be come like that. Big O of your this number of nodes, the square of that nodes. So suppose if you have 10 to the power 9 node, then you have 10 to the power 18 is your complexity. It will run for years and years, but it will never end. So that is the issue. Now next we will understand how to overcome that issue. You are getting with me? Like when we design these loss functions, what is the issue? Now next, we are trying to fix this issue. Step number 12. So as you said, that complexity, yeah. This one we have already explained. Now coming to step number 13. So instead of using this one, we will start the approximation one. So first one, normalization of softmax is culprit, because this is what we are seeing. So this is the culprit. So now let's do the approximation on this side. We need to approximate this. This can be done using a negative sampling. We do not take all the node, but a k node from the approximation for approximation, and instead of exponential function, we use sigmoid function for probability. So now how your similarity functions will change. Yeah, log of this is your original function. I'm writing it. Now this will be approximated log of I am using a sigmoid function. And instead of running through this entire graph, we will be only using k number of negative sampling. I will tell you what is negative sampling means. Sigmoid ZOP ZN. So we can write this is the log, so we can write it log of sigmoid ZUT ZB minus summation I equal to 1 to a, because this much we are doing log of sigmoid ZUT ZNI. This is what we are traveling. So here you can see you don't need to travel the entire graph, but just through the k sample we will see it how it is defined, and we are using this not exponential but the sigmoid function. So these approximations we have adopted. So by using k sample improves the efficiency of calculations. So let's write this point. This is also important thing to understand. So k sample yes sir. First point, higher k gives more robust estimate. So give more and more. Higher k corresponds to higher bias on the negative events. Next point. sample k negative nodes. Negative nodes, which is not part of your random walk actually. So all those nodes only we take it. Each with probability portion of its degree. So with the proportional of their degree, we take their uh, the probability is actually proportional to their degree. So naturality will happen. And what should be the good amount of the value? So k based upon the various experimentation like 15 to 20 is suggested. So you don't need to take in the millions. Okay. So usually negative sampling for any nodes done. So ideally you can take any node, but the most efficient way is to take the nodes which do not participate in your walk. So those kind of the nodes we take it. So this is about the negative sampling side. Point number 14. So once optimization function defined, then using gradient descents, we can optimize L. So now your optimization functions is defined by using this one. So this one you can place it over here, and then it is simplified approximation done. So after that, like you have already studied. So like any machine learning based gradient learning based method that we can use it. So we can use the gradient descent based method. For optimization of function L with respect to T. So this one we can use it, and you know that gradient descent method. So ZU, so this parameter can be understood by old ZU minus your learning rate by your gradient value. So through this, you can step by step adjust your weight as well. So by a stochastic gradient descent method, we can train ZU by optimizing L for the given training example. So that is where now. So whatever the data set you have, based on that, keep on computing your gradient and then adjusting the weight. So once you will have, so for each node, you will have a ZU based on this similarity functions. And once you will have, then this will be stacked in your matrix. And here you will have for each node, you will have d-dimensional vector set. And you can do the lookup in order to get their embedding. And from their embedding, you can perform various downstream tasks. We choose random walk because this is this is inexpensive method due to given higher probability to close a node. Other reason is we do not need to consider all pair node, but only those nodes which is participating in the random walk. So instead of for each and every pair of this entire graph, which is a traditional method, of getting the similarity score. So we are avoiding that, and we are using random walk based method. So we are saving a lot of computations by using this probability based approach. So this is the entire story of the random walk. Any question? All clear? Yes, no, anything? Anything? Asutosh or Nikunj?
We are good.
Good, all clear.
Yeah, so
Yes.
far.
Okay, good, Nikunj, good answer. Okay, so now we will coming to our next topic. That is the actually you can say extension of the existing node, that existing this algorithm that is called node to back. So initially, as I've hinted that here, only your strategy will change, and based on that we are computing the embedding. So now next one is your node to back method. So now questions comes, can we tune the random walk more so that embedding is more expressive? Initially uniform distributed we have adopted. Now we are talking how to make it more sophisticated. Okay, so how to make a random walk or deep walk more richer? So currently using uniformly distributed random walk, which may be too constant for downstream task. So our goal is to embed node such that similar network neighborhood should have embedding also closer. So maximizing likelihood optimizations, which is independent of downstream task. Only thing will change your strategy. So how we select the neighborhood? So this one we need to see here. So this time, instead of uniformly distributed random walk, we will choose second order biased random walk to choose neighborhoods. So second order biased random walk, this is what we will understand. So now understand second order random walk. If remember from where it came, previous state. So in the previously, we are not remembering. If you see, go back, then from X, we have come to Y position. Then at Y, we do not remember what is my previous position. So neighborhoods are defined based on the local and the global view of the network. So in this now what we are changing, we will remember this also, what is my previous positions, and we will see the local and the global view. Local view, global view. Local means micro. This is macro. And as I said, BFS has a capability of looking at the micro level, and DFS has a capability of looking at the global level. So BFS reflects your global view, BFS reflects your local view, DFS reflects your global view. So now fix the random walk length L for any random walk at the node U. So L is my I'm writing on this. Length of the random walk that we are giving. Okay, so based on the fixed length, we will generate neighborhood. So based on L, we will generate neighborhood of U. So for any node, what should be their neighborhood? This is what we will generate. So neighborhood are generally based on the two parameter here. We are using second order, so that is why here is the two parameter on which your neighborhood will depend. Two parameter P and Q. So here pay your attention. This is important parameter. So P is called your return back to previous state. Because as I said that we are remembering our previous state in this. So and Q is your in out parameter. This is trade-off between BFS and DFS. So in out parameter is what? This is trade-off between BFS and DFS. Intuitively, Q is the ratio of BFS versus DFS. So you can say this is the ratio. BFS versus DFS. So intuitively, this is the ratio. How much you want, like how much local and how much global. So with that, you control this. And if you want to return back, then you are using parameter P. So for any intermediate step, there will be three possible next move. So just assume any in intermediate step that we are. So from any step, there will be three options. What are the three options? First, return back to previous state. Because from any intermediate step, you can come back to your previous step or move to next step as per BFS move, which will keep the distance same with respect to the previous state. So from here, suppose it was a previous, you want to go this. So based on the BFS, so your distance will be same. So whatever the next step you take. So you will write it. So move to the next step as per the BFS move, which will keep distance, keep distance, keep the distance same, respectful previous state. So on the same level, we are just moving or move away. Another last option could be your move away from previous state. That will be your DFS. Okay. So by using Q, we are actually giving not uniform, but we are keeping it biased approach. So we create biases in the above move. By introducing P Q in transition probability. So let's understand the movement using one visualization. So here node U. So suppose this is the graph. From here, this is your starting point. This is your previous state. This is your current positions, and from here you have to make a move. Okay, this is the graph. So here, what is the probability? Like Q is your return back. So from the current position, this is my current position. From here, I have to make a move. So how to make a decision? So here C is some constant. So C by P probability that we will move it back. What will be the probability that we will be on the same level based on my previous state? So this one, this is the BFS move. So from here, this is the BFS distance. So distance will remain same. So this is the probability C we are taking. And what is the probability that we are moving away? So C by Q we are taking. So we can go to either this side or we can go to either this side. Both is actually moving away from this state. So this has become a 2 hop. So here also C by P. Okay. So we have moved from U to S1, S1 to W, and at W we are deciding which one will go? So there is a 4 possibility that go to S2, that is with the weightage of the same as constant C, return back to previous state S1 with the transitions weightage probability, that is the C by P, or go away. So go away means go to S3 or S4 with the transition weightage C by Q. So in your if you will use it, so this node to wake is already available in your Python library. So in this is what you have to mention. So the moment you make it P and Q equal to 1, that will become your random walk. Moment you give some probability, some biasness, then it will become a node to wake method. So this transition weightage is unnormalized distributions. We can normalize this. So right now this is unnormalized. So you can normalize this also. So normalization's value will be your C plus C by P plus C by Q. So this is the total summation. So each one if you divide, then you can normalize this also. And finally, I will take just a few more minutes. So W from W, you can move to S1 with the probability CP by S, or you can move to S2 with probability C by S. We can move to S3 with the probability C by Q by S, or you can move to S4 with probability C by Q by S. This is same. So based on the P and Q, you can guide this, your random walk, that, okay, who will be my neighborhood? So wherever you go, that becomes your neighborhood. So that way you are getting your neighborhoods. Okay, so based on this random walk, we generated neighborhood, and for each neighborhood and node U, we make R random walk of the length held to generate neighborhood of the U. So for this NRU, we will optimize node to wake objective functions using a stochastic gradient method. Since generations of the neighborhood for each node is independent, so we can parallelize the encoding of the functions to generate embedding. So this is important point, because here you can see. So for each node, the getting the neighborhood is independent function of the another node. So you don't need to do it one by one. So at a time, you can do the parallel generations for all the node, do the random walk simultaneously, and generate the random graphs and start optimizing it. So the time complexity of this algorithm becomes linear. So there are many other ways in which we can generate the embedding, like different kind of the random walks, or alternative optimization techniques, or network pre-positioning techniques. So these are the some of the other methods, those things you can use it. Scalability is issue, as it is a good up to medium size network, not for the very large network because of your shallow work. So that is where we are up to medium size network, means like in the millions, I think you can go. So this is what about the node to wake method. So any questions before we wrap up our today's session? If no questions, then we can close our today's session. I will share these things in chat window as well as in
Professor,
our.
should I close the recording?
Yeah, yes, sir.